So what is a smart safe? The smart safe is our idea to make a safe that can detect when it should lock. So this keeps all belongings safe but accessible when you need them, and it's safe when it detects an unsafe environment that will be shown later.
For this project, we used a flame sensor that detects heat and triggers the buzzer and locking system. We also used the water sensor that can detect a flood, in which case the safe will be locked. The keyboard was used as a security system to unlock and lock the safe, and the LED and buzzer sensors were used as visual and auditory elements to inform the user.
So why is this useful? This smart safe can be implemented into any home as it's just as compact and transportable as a regular safe is, but with even more security measures in place. So since the sensors can activate upon sensing any dangerous environments, the safe can be kept unlocked for ease of use. So for example, one can put their wallets inside the locked safe, an unlocked safe, and take it out when they want to, but if there were to be a dangerous environment like a fire or flood, the wallet would be locked because of the sensors. So let's look at the in-depth version of the flame sensor. So the flame sensor uses light sensing capabilities measured in luminosity intensity to gauge the safety of the safe. So a graph in LabVIEW shows how if the sensor senses light below 200 lumens, since the sensor works inversely if it senses light the values are lower, and it turns on an LED in the program, tells the buzzer to click on and say it's not safe. Then this will prompt the motor to lock the belongings. So here, a case structure and the in-range and coerce function were used to detect whether the conditions were safe while running the program. And here is the individual VI, as well as the individual graph with all of the various components written on it. So here's the flame sensor video along with a breadboard diagram of what it is. As you can see, when I got the lighter and moved it towards the breadboard, it was able to sense it and the graph adjusted appropriately and the not safe LED was flashing on as well as the buzzer clicking on, detecting that it's not a safe environment.
The water sensor can detect whether there is water and what level it is at. As shown in the VI, it uses voltage readings to do this. To portray this, a water tank was used to visually represent this data. Also, to the side, you will see the breadboard configuration for the sensor. This is the functioning water sensor, and as you can see, when the water sensor comes in contact with the water, the voltage increases.
We're going to talk about the keypad a little more. So the keypad was set up using a single analog input port, which was the A0 port on the Arduino. And then each one of the rows of columns have their own resistor at a different value, ranging from 1 kilo ohms to 30 kilo ohms. Meanwhile, a 5-volt current is ran through all the rows of columns. Because of this, because of the resistors, each one of the intersections of a row and column has a separate value. Then using a range and course block in LabVIEW, you're able to differentiate each button and assign it a value from 1 to 9. The pin after was simple by permanently making a value true and then using AND blocks to create a pin. So here on the right side, you can see the different range and coerce blocks for each one of the ranges of voltages for each button. Then we assigned a button using these case structures. And through this feedback right here, whichever button you want part of your combination, you can be permanently true. Then using these AND blocks, we created the correct pin. We'll create a true value for this right here, feeding into our array. Next, you can see a video here of how it operates. So the buttons that are not part of the combination will turn off and turn back on without permanently staying true. And then buttons 3, 2, 5, and 8, which is our combination in this case, they will permanently stay true until the whole combination is there, which makes the pin correct, LED turn on. If you look at the diagram on the right here, you can see the different resistors for each one of the rows and columns. So the first 4 are the rows, and then we have the 4 columns. Each one has a different resistor, and then they are all connected to each other. Now talking about the motor lock, which is our main locking mechanism. So the stepper motor uses a microcontroller to control each of the 4 coils, which are previously discussed in the proposal. There are 4 wires connected to digital inputs 8 to 11, and an external power source, which is our battery. The DC motor and the microcontroller are both connected to the ground of the Arduino. The way the block diagram was set up for the motor is by using a case structure that initiates the motor when a true value is received. That true value can come from the flame sensor, the water sensor, or from our combination. Then a microcontroller using the Arduino digital ports connects each of the coils in a designated order to power create a clockwise or counterclockwise motion. The duration of the motion is controlled using a separate case structure. You can see that right over here. So this first one is our duration of motion case structure, which will compare the counter, which is this right here, to the overall time that's spent. The counter turns on when the value of true is fed into here. Then we have the case structure for operating the motor. So each one of these values down here, the false, false, true, true, is for one of the motors. So this order right here will create a clockwise, or in case to open it, it will be counterclockwise motion. We'll talk about this more later. So here you have the 4 digital input ports, which is from 8 to 11. And this is the microcontroller or a DC motor. This attachment here will be able to let this open and close the door. And then now external power source. Here's a video of how it happens when it opens. We also have an LED here that indicates when it's locked and unlocked. When you put in a combination, this LED turns green and their motor begins to move to open the door. And here in the second video, we've got the same thing. When you press number 9, which is our initiation for closing the door, it will turn into the clockwise motion to close. Our final VI is a combination of all the VIs that you've seen so far into one giant control system, which will allow the Arduino to open and close the door based on its inputs. So here, we've got a rather complicated looking VI, but this first section right here is what we talked about earlier for the keypad, all the range and coerce blocks and the AND blocks and the permanent true values. This feeds into an array down here. Then we've got our water level sensor, our flame sensor right over here, and then our time, duration of opening, case structure, and our main case structure to open and close the door. Here we've got also the LEDs for the red and green. Taking a closer look at this array block right over here, this is the most important component here because all of the true and false values will feed into here. So if the flame sensor or the water sensor prove true, that means there's a danger. So it's also fed into here. This will close the door. And if the correct combination is fed into here, it will open the door. As well as for our locking mechanism, which is when you press number 9. So all of these are in here. Taking a closer look at the locking and unlocking mechanisms. So the case structure for opening the door, which is when the correct pin is entered, is for case 2, which looks like this. Then for cases 4, 16, and 32, which is in the bottom 9 press, our water sensor and a flame sensor, it's the opposite direction. Close the door. And that's everything from me.
The project did not go without fault. Some of the limitations included the flame sensor. The flame sensor detects light instead of heat, so it is not as accurate as a temperature sensor. The rotational sensor was meant to sense the position of the safe. However, this was not possible. And lastly, the water sensor was originally supposed to be working with the LED. However, we opted for it to work with the keyboard instead.
So the applications for research and industries can be found in the police or correctional facilities where valuables are often stored in safes, and those valuables are keys or tools, so the officers could rest easy in their offices knowing that the belongings and tools are kept safe if an emergency were to occur. And another industry is that the smart safe could thrive in the banking industry. So if there were ever to be a fire or flood, the main vaults would keep the money safe as the sensor would pick up on the heat or water levels. Of course, the sensor would have to be quite powerful and it would have to be very large as well as safe, but it could still work in this application.